In an era where humanity's reach extends far beyond the confines of Earth, a solitary spacecraft launched in the summer of 1977 has once again rewritten the boundaries of our understanding. NASA's Voyager 2, a relic of human ingenuity from an age of analog technology, has achieved what was once thought impossible. It has crossed the heliopause, the invisible boundary where the sun's influence wanes, and entered the vast, uncharted expanse of interstellar space. This monumental journey, spanning over 12 billion miles and nearly 5 decades, has delivered revelations that challenge the very foundations of astrophysics. The data streaming back from this intrepid probe paints a picture of a cosmic frontier that is not a quiet void, but a dynamic, mysterious realm pulsing with unexpected phenomena. From surging cosmic rays to strangely ordered magnetic fields, Voyager 2's findings are forcing scientists to rethink everything we thought we knew about the edge of our solar system. This is not just a story of exploration, it's a tale of cosmic wonder that demands we reimagine our place in the galaxy. Stay with us as we dive into the staggering discoveries that Voyager 2 has uncovered, revealing secrets that could redefine the universe as we know it. On August 20th, 1977, Voyager 2 embarked on a mission to explore the outer planets, carrying with it a golden record etched with the sounds and images of Earth, a message to the stars. Designed to study Jupiter, Saturn, Uranus, and Neptune, the spacecraft was never expected to survive this long, let alone venture into interstellar space. Yet in 2018, Voyager 2 crossed the heliopause, the boundary where the solar wind, a stream of charged particles from the sun, gives way to the interstellar medium, the sparse material that fills the space between stars. This crossing marked only the second time in history that a human-made object had entered this uncharted territory, following its twin, Voyager 1, in 2012. But what Voyager 2 found beyond this boundary was unlike anything scientists had anticipated. The heliopause, once thought to be a simple demarcation line, revealed itself to be a complex, dynamic frontier where the rules of physics seemed to bend in ways that defied decades of predictions. The heliosphere, the protective bubble created by the sun's solar wind, extends far beyond the orbit of Pluto, shielding our solar system from the harsh radiation of interstellar space. As Voyager 2 crossed this threshold, it entered a region where sunlight is a mere whisper, and the influence of the sun fades into the cosmic background. The data it transmitted back to Earth across a distance so vast that signals take over 17 hours to reach us, revealed a landscape of cosmic phenomena that no model had predicted, from magnetic fields that refuse to weaken to plasma behaving in ways never seen before. Voyager 2's findings have turned the edge of the solar system into a cosmic laboratory, challenging our understanding of the universe and igniting a firestorm of scientific curiosity. As Voyager 2 drifted deeper into interstellar space, its aging instruments began detecting anomalies that left scientists stunned. The spacecraft's sensors, designed in the 1970s with technology now considered archaic, were built to measure charged particles, cosmic rays, and magnetic fields. Yet the data they sent back didn't align with any existing models of interstellar space. Cosmic rays, high-energy particles from distant stars and galaxies, were expected to be evenly distributed in this region. Instead, Voyager 2 recorded strange waves of these particles, surging and receding in irregular pulses that defied explanation. The magnetic field, which scientists predicted would weaken and diffuse beyond the heliopause, grew stronger and more organized, with a field strength nearly 3 times greater than what Voyager 1 had observed years earlier. Even more perplexing, the direction of this magnetic field was entirely different from what was expected, suggesting that the interstellar environment might vary dramatically over short cosmic distances. Perhaps the most astonishing discovery was the behavior of the plasma, the hot ionized gas that permeates much of the universe. In the region beyond the heliopause, scientists expected to find sparse, sluggish plasma, a stark contrast to the dynamic solar wind within the heliosphere. Instead, Voyager 2 encountered a denser, colder plasma, caught in a strange liminal state that was neither fully solar nor interstellar. This unexpected buffer zone hinted at a previously undetected layer surrounding the solar system, a kind of interstellar sheath that separates our cosmic neighborhood from the broader galaxy. The plasma's behavior suggested it was influenced by forces far beyond the sun, raising questions about the true nature of the heliopause. Was this boundary a simple edge, or was it a dynamic reactive membrane shaped by interactions with the galactic environment? The magnetic field data from Voyager 2 added another layer of mystery to this cosmic puzzle. The spacecraft's onboard magnetometer recorded a sharp increase in field strength as it crossed the heliopause, a phenomenon no simulation had ever predicted. This wasn't a fleeting glitch. The data showed a consistent, patterned increase in magnetic intensity, suggesting the presence of an organized structure in what was thought to be chaotic interstellar space. Even more intriguing, Voyager 2 detected rapid changes in magnetic polarity, events known as magnetic reconnection, where field lines snap and realign, releasing bursts of energy. Such events are typically associated with powerful stellar phenomena, like solar flares or the intense environments near black holes. To find them occurring in the supposedly calm expanse beyond the solar system was nothing short of revolutionary. These magnetic anomalies pointed to a startling possibility. The edge of the solar system might be a region of fierce electromagnetic activity, driven not just by the sun, but by interactions with the broader galactic environment. The data suggested that the heliopause could be more than a passive boundary. It might be a frontier where solar and interstellar forces collide, creating a dynamic interplay of energy and matter. This idea was further supported by the strange behavior of radio waves detected by Voyager 2. The spacecraft's periodic signals back to Earth began to show subtle distortions, with frequency shifts and phase modulations that hinted at complex structures in the plasma, like eddies or folds in the fabric of space. These weren't the random variations expected in a uniform interstellar medium. They suggested a layered, dynamic structure at the solar system's edge, one that might even possess protective properties. One of the most perplexing findings from Voyager 2 was the unexpected directional shift in cosmic ray distribution. The spacecraft's cosmic ray detector revealed a persistent asymmetry. More high-energy particles were arriving from one direction than any other, a pattern that defied the isotropic models of interstellar space. These particles weren't of solar origin. They were galactic, possibly even extragalactic, yet they appeared to be focused, as if guided by an invisible lens or filter. This directional bias suggested the presence of a massive magnetic structure or gravitational feature in interstellar space, capable of altering the trajectories of these high-energy particles. Such a mechanism, if confirmed, would indicate that the solar system is surrounded by an unseen force field, perhaps a relic of the galaxy's magnetic topology, or something even more exotic. This discovery led to bold but scientifically grounded speculation. Could the sun's motion through the Milky Way be creating a magnetic wake, like a boat stirring ripples across a lake? If so, Voyager 2 might have entered this wake, encountering a region where magnetic fields converge and twist. Alternatively, the galaxy itself could be threaded with vast magnetic filaments, cosmic scaffolding that influences plasma and particles across immense distances. The idea that interstellar space is structured and dynamic rather than a featureless void challenges long-held assumptions about the interstellar medium. It suggests that our solar system is not an isolated bubble, but an active participant in a larger galactic ecosystem, shaped by forces we are only beginning to understand. The plasma discoveries made by Voyager 2 are perhaps the most revolutionary of all. The denser, colder plasma it encountered didn't behave like the solar wind, nor did it match the characteristics of interstellar plasma. Instead, it existed in a strange hybrid state, caught between two worlds. This unexpected plasma raised immediate questions about the nature of the heliopause. Could it be a transformative zone, where solar material undergoes a mysterious transition as it merges with the interstellar medium? The idea of a third kind of plasma, one that is neither solar nor interstellar, is entirely novel and could represent a new state of matter, existing only in the boundary regions of star systems. If confirmed, this discovery could redefine how we classify cosmic matter and open new avenues in plasma physics. The implications of this finding extend far beyond astrophysics. If the heliopause acts as a cosmic crucible where unique chemical and physical processes occur, it could be a birthplace for the building blocks of life. The interaction of radiation, cold plasma, and interstellar dust in this region might catalyze the formation of organic precursors, molecules that could seed future planetary systems. This possibility adds a profound dimension to Voyager 2's discoveries, suggesting that the edge of the solar system is not just a boundary, but a zone of cosmic synthesis, where the raw materials of life might be forged. Voyager 2's data also points to a broader, more dynamic relationship between the solar system and the galaxy. For decades, scientists viewed the heliopause as a static edge, a point where the sun's influence ended and interstellar space began. But Voyager 2's findings reveal a boundary that is far from passive. The heliopause appears to be a semi-permeable, reactive membrane shaped by interactions with galactic magnetic fields, gas clouds, and possibly even dark matter. This dynamic boundary could act as a cosmic weather shield, bending and redirecting cosmic rays to protect the inner planets from harmful radiation. However, this shield is not constant. As the solar system moves through the galaxy, encountering different interstellar environments, the heliopause may shift, exposing Earth to varying levels of radiation. These shifts could have profound implications for our planet. Changes in cosmic ray exposure might influence Earth's climate, biological evolution, or even trigger mass extinctions over geological timescales. The idea that galactic-scale forces could leave signatures in Earth's geological record, in ice cores, tree rings, or fossil layers, adds a new layer of complexity to our understanding of planetary science. Voyager 2's discoveries suggest that our solar system is not an isolated entity, but a dynamic participant in a vast galactic ecosystem, constantly reshaped by its cosmic surroundings. The complexity of the heliopause revealed by Voyager 2 extends to the discovery of unseen structures in interstellar space. The spacecraft detected what appeared to be temporal oscillations in particle density, cyclic changes that suggest a pulsing or beating pattern in the interstellar medium. These pulsations don't align with known solar or galactic phenomena, hinting at a source of regular influence operating on scales previously unaccounted for. Some scientists speculate that these oscillations could be evidence of the solar system moving through a structured wave of interstellar gas, perhaps a ripple in the Milky Way's spiral arm caused by ancient gravitational perturbations or exotic matter distributions such as dark matter filaments. Voyager 2 also recorded low-frequency electromagnetic tones within the plasma, deep humming oscillations that suggest massive coherence among particles. These plasma tones, when converted to sound waves, form complex patterns reminiscent of standing waves in confined systems. Their existence implies that the interstellar medium is not a chaotic void, but a structured, resonant medium capable of supporting stable, large-scale features. If these coherent structures exist, they could offer a natural form of propulsion for future spacecraft, allowing them to surf these waves for low-energy travel. More immediately, their discovery transforms our understanding of interstellar space, revealing it to be a dynamic, organized realm rich with invisible harmonies. Among Voyager 2's most evocative discoveries are the detection of compressional waves, pressure disturbances in the plasma that behave like seismic waves in a solid medium. Dubbed plasma quakes by some scientists, these ripples carry information about the density and elasticity of the interstellar medium, suggesting that space itself has acoustic properties. This revelation transforms our perception of the cosmos from an airy void to a medium capable of vibrating and resonating with celestial scale disturbances. These plasma quakes could be triggered by distant events, such as supernovae or galactic magnetic oscillations, and their persistence across vast distances hints at a highly structured interstellar environment. Equally astonishing is the evidence of interstellar jet streams, looping quasi-circular paths of high-energy particles that ebb and swell over time. Unlike the solar wind, which is driven by the sun, these jet streams appear to be governed by galactic-scale pressure gradients, forming dynamic currents and eddies that defy the notion of empty space. These discoveries suggest that the outer solar system is laced with invisible flows, reminiscent of atmospheric jet streams on Earth, but operating on a cosmic scale. The presence of such structured flows challenges our models of energy transport in space, suggesting that diffusion and dissipation occur in pulses or sheets rather than smooth gradients. Voyager 2's spectral analysis has uncovered another layer of intrigue, the detection of unexpected ion species and dust grains in interstellar space. The spacecraft found higher than expected concentrations of negatively charged oxygen ions, as well as traces of iron and nickel nuclei at energies that suggest a non-local origin. These ions are likely the remnants of ancient supernovae carried across the galaxy by cosmic winds over millions of years. Their presence in Voyager 2's vicinity indicates that the outer solar system is a chemical melting pot enriched by the byproducts of long-extinct stars. This discovery adds a poetic resonance to the mission. Voyager 2, a machine built from stardust, is now traversing the ash of cosmic explosions that predate our sun. The dust grains detected by Voyager 2 are equally fascinating. Smaller and more irregular than those found within the heliosphere, these grains are coated with layers of unknown origin, possibly organic films or frozen volatiles never before cataloged. As As they interact with the magnetic and plasma environment, these grains charge up and behave like miniature projectiles, triggering secondary emissions that Voyager 2's instruments can detect. These interactions open a new field of study in dust-plasma coupling, a process that could play a critical role in galactic evolution and the formation of planetary systems. Voyager 2's discoveries are not just scientific, they are profoundly philosophical. The heliopause, once seen as a clear boundary between the solar system and interstellar space, is now revealed to be a liminal zone, neither fully inside nor outside. This raises fundamental questions about the nature of boundaries themselves. If the heliopause is a dynamic, reactive membrane constantly shaped by galactic forces, then what does it mean to exit the solar system? Perhaps there is no true outside, only varying degrees of connectivity between the sun and its galactic surroundings. This perspective could redefine the solar system, broadening it to include layers of influence that extend far beyond traditional definitions. The complexity of this frontier demands new mathematical tools and models. Fluid dynamics, magnetic field theory, and plasma physics are being retooled to incorporate non-linear and non-equilibrium processes, as Voyager 2's data reveals a chaotic richness that older symmetrical models failed to capture. These evolving models will shape the future of space travel, astrophysical research, and our understanding of the forces that govern star systems and planetary evolution. The idea of zones of influence, regions where stellar and galactic forces create unique conditions, is gaining traction, and Voyager 2's findings suggest that the heliopause is one such zone, a cosmic crucible where novel physical and chemical processes unfold. Voyager 2's journey is a testament to human curiosity and resilience. Launched during the Cold War, equipped with technology now considered primitive, the spacecraft was never meant to deliver such profound revelations this late in its life. Yet, its endurance and the clarity of its discoveries remind us that the quest for knowledge transcends time and technology. Each data packet sent across the cosmic void is a spark from a machine older than most people alive, yet more relevant now than ever. Voyager 2 is not just an observer, it is a narrator, telling a story of complexity, contradiction, and cosmic wonder at the threshold of our solar system. The discoveries made by Voyager 2 have initiated an entirely new domain of inquiry, one that was previously considered irrelevant because it was deemed impossible. The flow of particles, the pressure gradients, the waveforms of energetic electrons, and the peculiar interactions among magnetic fields are all behaving in unprecedented ways. These findings suggest that the heliopause is not a passive border but a transformative zone, where solar material merges with the interstellar medium in ways we are only beginning to understand. The implications for planetary science, cosmology, and even the search for life are profound, as Voyager 2's data hints at a universe far more interconnected and dynamic than we ever imagined. Voyager 2's journey has unveiled another layer of cosmic intrigue: the detection of shockwave echoes, delayed ripples in particle density, and magnetic field disturbances that appear to be remnants of ancient solar events. These echoes, likely triggered by solar flares or coronal mass ejections years ago, have traveled immense distances, bouncing through the interstellar medium before reaching Voyager 2. This temporal stretching suggests that interstellar space acts as a vast resonant chamber, capable of storing and reshaping energetic waves far beyond previous estimates. Unlike the turbulent heliosheath just inside the heliopause, where solar wind slows and interacts with the interstellar medium, this outer region exhibits a paradoxical blend of stability and activity, with enormous plasma structures that remain consistent over time while hosting unpredictable surges of energetic particles. These shockwave echoes hint at a universe that retains a memory of its past, where events from decades or even centuries ago continue to ripple through the cosmos. The discovery challenges our understanding of how energy propagates in interstellar space, suggesting that the medium is not a simple vacuum, but a complex resonant system capable of preserving and amplifying signals over vast distances. For scientists, this opens a new avenue of research into the temporal dynamics of the interstellar medium, potentially allowing us to trace the history of solar activity and its interaction with the galaxy. For humanity, it's a humbling reminder that even our sun's fleeting outbursts can leave lasting imprints on the cosmic landscape, connecting our solar system to the broader universe in ways we are only beginning to comprehend. Among Voyager 2's most striking discoveries is the evidence of interstellar jet streams, looping, quasi-circular paths of high-energy particles that ebb and swell over time, reminiscent of atmospheric jet streams on Earth. Unlike the solar wind, which is driven directly by the sun, these interstellar flows appear to be governed by galactic-scale pressure gradients, forming dynamic currents and eddies that defy the notion of empty space. The presence of these structured flows suggests that the outer solar system is laced with invisible currents, operating on a cosmic scale and driven by forces far beyond our star. Voyager 2's detection of these jet streams has revealed a dynamic system of particle drifts with distinct flow regimes, density boundaries, and temperature differentials that were invisible until now. The discovery of these jet streams has profound implications for our understanding of energy transport in space. Rather than smooth gradients, energy appears to cascade in pulses or sheets, driven by the interplay of magnetic fields and plasma dynamics. This structured turbulence, characterized by stripes of intense activity interspersed with calmer regions, challenges existing models of diffusion and dissipation in the interstellar medium. For future space exploration, these jet streams could offer a natural form of propulsion, allowing spacecraft to harness their energy for low-energy travel across vast distances. More immediately, they transform our perception of interstellar space, revealing it to be a vibrant, dynamic realm where invisible forces shape the flow of matter and energy on a galactic scale. Voyager 2's spectral analysis has uncovered a chemical treasure trove in interstellar space, with the detection of unexpected ion species and dust grains that hint at the region's complex history. The spacecraft has recorded higher than expected concentrations of negatively charged oxygen ions, as well as anomalous traces of iron and nickel nuclei, at energies that suggest origins far beyond our solar system. These ions are likely the remnants of ancient supernova, carried across the galaxy by cosmic winds over millions of years. Their presence in Voyager 2's vicinity indicates that the outer solar system is a chemical melting pot, enriched by the byproducts of long-extinct stars. This discovery adds a poetic resonance to the mission. Voyager 2, a machine built from the stardust of our own star, is now traversing the ash of cosmic explosions that predate the sun itself. The dust grains detected by Voyager 2 are equally intriguing. Smaller and more irregular than those found within the heliosphere, these grains are coated with layers of unknown origin, possibly organic films or frozen volatiles never before cataloged. As they interact with the magnetic and plasma environment, these grains charge up and behave like miniature projectiles, triggering secondary emissions that Voyager 2's instruments can detect. These interactions open a new field of study in dust-plasma coupling, a process that could play a critical role in galactic evolution and the formation of planetary systems. The presence of such complex chemistry at the edge of the solar system suggests that this region is not merely a boundary, but a cosmic laboratory where the building blocks of future worlds are forged in the interplay of radiation, plasma, and interstellar dust. One of Voyager 2's most evocative discoveries is the detection of compressional waves in the interstellar plasma, dubbed plasma quakes by some scientists. These pressure disturbances behave like seismic waves in a solid medium, rippling outward from unknown epicenters and carrying detailed information about the density and elasticity of the interstellar medium. Their existence suggests that space itself has acoustic properties capable of vibrating and resonating with celestial scale disturbances. These plasma quakes could be triggered by distant events, such as supernovae, galactic magnetic oscillations, or even the passage of the solar system through dense interstellar clouds. Their persistence across vast distances hints at a highly structured interstellar environment where energy and information are transmitted in ways we are only beginning to understand. The discovery of these plasma quakes transforms our perception of the cosmos, from an airy void to a medium capable of echoing with the vibrations of distant events. This revelation opens new possibilities for studying the interstellar medium, as these waves could carry signatures of ancient cosmic phenomena, allowing scientists to probe the history of the galaxy. For future missions, the ability to detect and interpret these plasma quakes could provide a novel method for mapping the structure of interstellar space, revealing hidden features like magnetic filaments or shock fronts. The idea that space can sing with these cosmic resonances adds a layer of wonder to Voyager 2's journey, reminding us that the universe is a dynamic, interconnected system, alive with invisible harmonies. Voyager 2's findings have also sparked speculation about the role of dark matter in shaping the interstellar environment. While dark matter remains undetected directly, some hypotheses suggest it could cluster in filaments or halo-like distributions around galaxies, subtly warping space-time or altering magnetic field propagation. The anomalies detected by Voyager 2, such as the unexpected directional bias in cosmic rays or the structured magnetic fields, could be influenced by such dark matter structures if they exist in our region of the Milky Way. This possibility, while speculative, adds a new layer of urgency to the interpretation of Voyager 2's data, as it offers a rare opportunity to study dark matter's effects through its indirect influence on interstellar plasma and magnetic fields. If dark matter is indeed shaping the heliopause, it could have far-reaching implications for our understanding of the galaxy. The heliopause might act as a natural laboratory for studying dark matter's interactions with ordinary matter, providing clues about its distribution and behavior. This could bridge the gap between astrophysics and cosmology, offering insights into the invisible forces that govern the large-scale structure of the universe. Voyager 2's data, though limited by its aging instruments, is pushing the boundaries of what we believe is possible, prompting scientists to consider that the edge of the solar system might hold the key to unlocking one of the greatest mysteries of modern science. The heliopause, as revealed by Voyager 2, is emerging as a cosmic crucible where new physics may be born. The spacecraft's detection of wave-particle interactions, where particles ride along magnetic or electric field waves to accelerate or decelerate, has unveiled a phenomenon previously thought to occur only near strong gravitational or electromagnetic sources, like stars or black holes. Yet Voyager 2 has captured a new kind of wave-particle resonance, one that siphons energy from one particle population to another without the usual thermal signatures. This mechanism, unique to the hybrid zone at the heliopause, suggests the presence of stable, guiding structures, possibly filamentary magnetic fields or large-scale electric field configurations sustained by galactic currents. These discoveries point to the possibility of entirely new physical processes, ones that could redefine our understanding of energy transfer and matter interactions in the cosmos. The heliopause's unique conditions, where solar and interstellar forces meld, may create an environment where novel states of matter or energy emerge, challenging the limits of our current theories. For scientists, this is an exhilarating prospect, as it suggests that the edge of the solar system is not just a boundary, but a frontier of discovery, where the interplay of plasma, magnetic fields, and cosmic rays could unlock new laws of physics. Voyager 2's journey through this enigmatic zone is not just a scientific milestone, it's a bold step into the unknown, where the universe itself may reveal its deepest secrets. As Voyager 2 continues its lonely journey, drifting further into the interstellar void, it carries with it the hopes and dreams of a species reaching for the stars. Its discoveries have overturned long-standing assumptions, revealing a cosmic frontier that is alive with invisible forces, resonant structures, and chemical surprises. The heliopause, once thought to be a quiet horizon, is now a dynamic realm filled with phenomena we barely comprehend. With each signal it sends home, Voyager 2 challenges us to rethink our place in the cosmos, not just as inhabitants of a solar system, but as participants in a vast galactic tapestry. The questions raised by Voyager 2 are timeless. What lies beyond the known? How do the forces of the galaxy shape our world? And what does it mean to explore a universe that is both familiar and utterly alien? As we ponder these mysteries, Voyager 2's legacy grows, not because it provides clear answers, but because it asks better questions. It reminds us that the edge of the solar system is not an ending, but a beginning, a gateway to a universe filled with wonder, waiting to be explored. So let's keep watching the skies, for Voyager 2's impossible discoveries are just the start of a cosmic journey that will redefine our understanding of the stars and our place among them.